A data center is not cooled when the room average thermometer looks comfortable. It is cooled when every server inlet stays inside the approved environmental envelope. A single high-density rack can ingest hot recirculated air while a wall sensor reports a normal value. Start the design at the equipment inlet, and treat the hottest inlet, not the average return temperature, as the boundary that must be protected. Before drawing an airflow map, draw the load map. Record heat by row, rack, and height, and separate the air-cooled share from heat removed by liquid. Two rooms with the same total kilowatts can need different air routes when one has evenly distributed racks and the other has a few high-density islands. The load schedule also has to include growth states, maintenance states, and the combinations that can actually occur. Now convert the air-cooled sensible heat into a first airflow estimate. In this teaching example, 500 kilowatts are assigned to air cooling. With inlet air density of 1.18 kilograms per cubic meter, specific heat of 1.006 kilojoules per kilogram Kelvin and a 12 Kelvin rack air temperature rise, volume flow equals heat divided by density, specific heat and temperature rise. The result is 35.1 cubic meters per second, or about 126,000 cubic meters per hour. This is an energy balance, not a finished fan schedule. Real density, leakage, load distribution, and inlet limits still matter. Next, give the air one clean direction. Cold supply air must reach the equipment intake, cross the IT load once, and leave through the hot return path. Rack orientation, blanking panels, raised floor or overhead delivery, containment and return placement all serve that route. More fan airflow cannot repair a path that sends supply air around the servers or lets hot exhaust turn back into the next inlet. There are two different shortcuts to close. Recirculation is hot exhaust returning to equipment inlets. It raises local inlet temperature. Bypass is cold supply returning to the cooling unit without removing IT heat. It wastes delivered airflow. Seal unused rack spaces and cable openings, match diffusers to rack demand, and verify containment leakage. Fix the route before increasing speed, because extra airflow can strengthen the wrong shortcut. Fans must then be selected at airflow and pressure together. Build a pressure ledger at the same design flow. This illustrative path includes 120 pascals for filters, 240 for the coil, 110 for the plenum, 90 for diffusers, 70 for containment and 170 for the return path, 800 pascals in total. Replace every example number with project data, and define clean, loaded and abnormal states. The actual fan/system intersection, not free air maximum flow, sets delivered airflow. For an array, normal sharing is only the first point. Remove one module, include the real isolation or backflow condition, and calculate the common pressure point for the remaining fans. In this example, the failure target is still about 126,000 cubic meters per hour, but that is a requirement to prove, not an automatic property of N+1. Check the remaining speed, absorbed power, current, sound and stable operating range on verified curves. A spare module that forces every survivor beyond its limit is not usable redundancy. Redundancy is also a time and temperature response. A fan module failure, an entire cooling unit failure, a power path failure and a controller failure have different consequences and may share common causes. Define detection time, alarm delay, speed redistribution, available thermal buffer and the hottest inlet trajectory. Module level coverage does not prove cooling unit, electrical or controls resilience. Test each failure class against the project availability objective. Control from measurements that represent the risk. Place temperature sensors at the top, middle and bottom of representative rack inlets, especially near high density and end of row positions. Combine them with containment differential pressure, fan speed, current, unit status and alarm trends. A return air sensor can support control, but it cannot replace inlet visibility. Define which signal leads, how bad data is rejected, what happens after communication loss and how overrides are recorded. Then fit the strategy into serviceable hardware. The moving Longwell fan wall footage shows a real modular arrangement, but it does not prove this example's airflow or pressure. Use it to inspect module spacing, inlet clearance, frame stiffness, power and control routing, safe isolation, lifting access and replacement direction. Confirm that a module can be removed without exposing personnel or allowing uncontrolled reverse flow, and that the selected fan curve covers every scheduled state. Commission the normal state and the failure state. Verify airflow direction, rack blanking and load assumptions, measure pressure and rack inlet temperatures, command one fan out and, where the approved test plan permits, one cooling unit out, record alarm timing, redistribution, power limits and thermal recovery. Repeat for control and power path scenarios that are in scope. The acceptance result is evidence at the equipment inlet, not simply a green status icon on the cooling unit. Release one reviewable cooling schedule, rack load map, approved inlet envelope, airflow equation and density basis, supply and return routes, leakage assumption, pressure ledger, verified fan curves, normal and failure operating points, control architecture and functional test plan. Only after those fields agree should the equipment selection be frozen. For a project-specific review, send Longwell the load map, airflow and pressure states, electrical/control requirements and installation geometry.